Hello everyone. Today we are going to discuss about visualizing convolutional neural networks. Why is it so important to visualize convolutional neural networks? Let us start the session. One of the most debated topics in deep learning is how to interpret and understand a trained model. Particularly in the context of high-risk industries like healthcare, the term black box has been often associated with the deep learning algorithms. How can we trust the result of a model if we can't explain how it works? It's a question, right? Let us take an example of a deep learning model trained for detecting cancer's tumor. This model tells that it is 90% sure, 99% sure that it has detected the cancer. But it does not tell why or how it had made the decision. So, if a model tells that it is 99% sure that it has detected the cancer, it doesn't tell how or why it has made the decision, right? Did it find any important clue in the MRI scan, or it is just a smudge on the scan that was incorrectly detected as a tumor? This is the matter of life and death of a patient, and doctor cannot afford to be wrong. Importance of visualizing a CNN model. As we have seen in the cancerous tumor example above, it is an absolutely crucial that we know what our model is doing and how it is making decision on its predictions. Typically, the reasons listed below are the most important points for a deep learning practitioner to remember. The important points are the important points one should remember are understand how the model works, and second thing is assistance in hyperparameter tuning. Third one is finding out the failures of the model and getting an intuition of why they failed. Fourth one, explain the decisions to a consumer or an end user or a business executive. These are the points one should remember. Let us look at an example where visualizing a neural network model helped in understanding the faults and improving the performance. Once upon a time, the US Army wanted to use neural network to automatically detect camouflage enemy tanks. The researchers trained a neural net on 50 photos of camouflage tanks in trees and 50 photos of trees without tanks. Using standard techniques for supervised learning, the researchers trained the neural network to a weighting that currently loaded the training set output yes for the 50 photos of camouflage tank and output no for the photos of the forest. So, the US Army had used an artificial neural networks to detect the camouflaged enemy tanks. So, they have taken the 50 photos of camouflaged tanks along with the trees and 50 photos of forest with the trees. So, they have trained the model using 50 photos of different things. And this did not ensure or evenly imply that new examples would be classified correctly. The neural network might have learned 100 special classes that would not generalize to any new problem. Wisely, the researchers had taken originally 200 photos, 100 photos of tank and 100 photos of trees. They used only 50 of each for training set. The researchers ran the neural network on the remaining 100 photos. And without any further training, the neural network classified all the remaining photos correctly. The success has been confirmed. The researchers handed the finished work to a Pentagon, which soon handed it back, complaining that in their own test, the neural network did not do any better than chance at discriminating photos. It turned out in researchers' dataset, photos of camouflaged tanks had been taken on a cloudy days, while photos of plain forest had been taken on sunny days. The neural network had learned to distinguish cloudy days from sunny days instead of distinguishing camouflaged tanks from an empty forest. So it has turned out the model is detecting the sunny days from the cloudy days. Why is it so? Because the photos were taken on the sunny day for the forest, and the photos were taken on a cloudy days for the camouflaged tank. So the model has learned the unimportant thing rather than learning about the important thing. So it is very important to visualize a neural network whether it is learning correctly or not and whether it is predicting correctly or not. So it is an important thing to understand why our model is predicting particular thing. So it is important to visualize convolutional neural networks. Let us see the important methods of convolutional neural networks. In Let us see the important methods to visualize convolutional neural networks. Methods of visualizing a convolutional neural networks. Broadly, the methods of visualizing a convolutional neural network model can be categorized into three parts based on internal workings. First one is preliminary methods. Simple method which shows us the overall structure of a trained model. It's nothing but visualizing the overall architecture of a model that we have trained. And second one is activation based methods. In these methods, we discover that the activation of an individual neuron or a group of neurons to get off intuition of what they are doing. So we need to know what the model is exactly doing and how it is making the decisions. Third one is gradient based methods. These methods tend to manipulate the gradients that are formed from a forward and backward path while training a model. First one is preliminary method. This first subsection is plotting a model architecture. The simplest thing you can do is to print or plot the model. Here you can see also print the shape of individual layers of neural network and the parameters in each layer. So we will be able to visualize the overall architecture of our model. That means what are the layers, what are the all layers that are present in our model, and what is the shape of individual layer, and what are the how many number of parameters are present in the each layer. So we need to get a brief idea of a number of layers and then shape and the parameters. So we will be visualizing the overall architecture of our model. In Keras, you can implement it as model dot summary. So we'd be able to visualize the layers and the shape and number of parameters. Uh, the other subsection is visualize filters. Another way is to plot the filters of a trained model so that we can understand the behavior of those filters. For example, the first filter or first layer of the above model looks like this, and the syntax for the visualizing the filters of a top layer of our model is top layer is equal to model dot layers of 0, and we can plot that using this two lines. It is a syntax. Generally, we can see that the low-level filters as the edge detectors, and we go higher, then we tend to capture higher-level concepts like object and images. Second one is activation maps, maximal activations. To see what our neural network is doing, we can apply the filters over an input image and then plot the output. This allowed us to understand what sort of input patterns activate a particular filter. For example, there could be a face filter that activates when it gets the presence of a face in the image. It's nothing but an image detection. To see what our network is doing, we can apply the filters over an input image and then plot the output. So this can allow us to understand what sort of input patterns activate a particular filter. For example, there could be a face filter that activates when it gets the presence of a face in an object. Or else let us see the few more examples. When you see a mask on your face, it gets activated and it will show the presence of the mask in the image. In such a way, we should be able to do that. 2.2 Image occlusion. In an image classification problem, the question if the model is truly identifying the location of the objects in the image or it is just using the surrounding context. So we took a brief look at these gradient based methods above. So in the previous example, we have seen that a group of researchers have trained a neural network model using 50 photos of forest with the trees and 50 photos of camouflaged tanks with the trees. So as we have seen in the example that the model is able to predict correctly, but the model has trained based upon surrounding context, not exactly on the camouflaged tanks. It is able to detect whether it is a cloudy day or sunny day rather than telling if there is camouflage tank present or not. So it has learned the surrounding context instead of learning the object detection kind of thing. So we took a brief look at this in the gradient based methods above. Occlusion based methods attempt to answer this question by systematically uploading different portions of the input image with a gray square and monitoring the output of the classifiers. The example clearly shows the model is localizing the objects within the scene, as the probability of correct class drops significantly when the object is uploaded. So let us understand this concept by taking the random image from our dataset, try to plot a heat map of the image. This will give us an intuition of which part of the image are important for the model in order to make a clear distinction of the actual class. So here we are trying to do nothing but taking a random image from our data set and plot a heat map so that we will be able to know which part of the image is it considering important to predict output. So as we can see here, an input image is dog and a dog is holding a thing, and the our model should actually learn whether it is a dog or not, but our model is learning about the thing that is held by dog. The strong feature map shows that it is concentrating on a thing but not the dog. So our model we can one should be able to know what our model is uh, considering the important as important in order to predict the output. Third one, gradient based method, saliency maps. As we have seen in the examples of tank, how can we get to know which part does our model focuses on to get the prediction? For this we use saliency maps. Saliency maps first introduced in this paper. Deep inside convolutional neural networks, visualizing image classification model and saliency maps. As we have seen in the above example, in the example of a military tanks, the camouflage tanks and the trace. So one should be able to know on which part does our model focuses on to get the prediction. So for that purpose, the saliency maps were used. The concept of saliency maps is pretty straightforward. We compute the gradient of the output category with respect to the input image. We should one should actually compute the gradient of the output category with respect to the input image. This should tell us how the output category values change with respect to the small changes in the in the input image pixels. All the positive values in the gradient tell us that a small change to the pixel will increase the output value. Hence, visualizing these gradients, which are the same purpose as the image, which has the same shape as the image, should provide some intuition of attention. Intuitively, this method highlights the silent image regions that contribute the most towards the output. Gradient based class activation maps. Class activation maps or grade cam is another way of visualizing what our model looks like at while making predictions instead of using gradients with respect to output. GradCam uses penultimate convolutional neural network. This is done to utilize the special information that is being stored in the penultimate layer. So these are all the important methods of visualizing convolutional neural networks. it, the thing is it is important to visualize convolutional neural networks because we should know how our model is able to predict or what important features it has considered to predict the output. One should definitely know it, or else our prediction may be wrong. And as we have seen in the above two examples, one is the US military example, and the other one is in the cancerous tumor detection. So, in the healthcare industry, we cannot afford to be wrong. We cannot be sure. If the model is 99% sure, we can't be able to tell whether there is a cancerous tumor or not. The model should be 100% sure and it should predict correctly as it is life and death matter. In the case of US military case, model should learn. We should know what our model has considered to predict the output before before predicting the output. So it is important to visualize convolutional neural networks. That is now. Thank you.